So we are ready to start the second part or after lunch part of our workshop. Thank you all for attending it. And before starting and before giving the word to Pedro, I will just remark that we have 2 slots. They will be divided by a coffee break. And in this first slot, we will have Professor Luís Branco and Professor José Esperança, both from REQUIMTE and from the new University of Lisbon. And both of them, and most of you know them very well, they are experts on the ionic liquids field. And I think we will learn a lot with them. So thank you both for accepting our invitation and for being available to give us the talks. And now, Pedro, you are the chair.
Well, thank you very much, Mara. Welcome from after lunch. Let's start our session. It's a pleasure to me to be here sharing this session on new perspectives with ionic liquid, with 2 persons that are been sharing this amazing path with ionic liquids almost since the beginning of the boom on interest on ionic liquids. Our first speaker is Professor Luís Branco. Most of you already know him very well. He's been present in our group quite a bit. Professor Luís Branco is Assistant Professor and Principal Researcher at FCT, or Faculdade de Ciência e Tecnologia, Nova, and in the lab REQUIMTE is also the director of Solquemar, a Portuguese company that's founded in 2004 that has developed and commercializes several types of sustainable products, including ionic liquids, dipyrotic solvents, catalysts, and nanomaterials. In fact, most of you already know Solquemar. We kind of order several ionic liquids from them. Solquemar is the biggest producer of ionic liquids from South Europe and top 10 in the world. Professor Luís Branco research interests include the development of more sustainable synthetic strategies, including novel approaches for asymmetric catalysis, as well as novel platforms for pharmaceutical chemistry. And today we have the pleasure to hear a talk about ionic liquids as active pharmaceutical ingredients. And the floor is yours. Thanks.
Okay, good afternoon. First of all, thank you for your kind introduction, and also thanks the organizers of this workshop for the invitation to be here and to talk a little about our work. And for today, I would like to talk about task-specific ionic liquids for pharmaceutical applications. And we are working in a green chemistry lab named REQUIMTE, and in this laboratory we are trying to develop functional innovative salts for sustainability. And in particular, we are focused in ionic liquids and more recent in euthetic mixtures, and depending on the point of view and the composition, it's possible to consider as green solvents or green materials. Ionic liquids, many of you know the general definition. They are organic salts that are liquids until 100 degrees Celsius, and they are formed by the adequate combination of organic cations with anions. And the most important properties that I would like to emphasize from ionic liquids, the almost negligible vapor pressure and the high thermal and chemical stability. But the most important point and the most important characteristics that we are trying to play in order to design task-specific ionic liquid, it's the possibility to tune their physical and structural properties, and this is dependent of the adequate combination of organic cations and anions. In last decades, the evolution of ionic liquids can be summarized in different generations as alternative solvents in the beginning, then as advanced materials, and more recent, incorporating pharmaceuticals and biological properties. In our lab, we are working in these different generations. We are working in bio-inspired ionic liquids based on biological molecules for chiral recognition, for catalysis. We are working in functional materials and in particular in stimuli-responsive ionic materials, and more recent, trying to incorporate active pharmaceutical drugs as cation or anion in the structure of ionic liquids. And looking for pharmaceutical drugs, we know some of the problems associated to the drugs, like the polymorphism. It is one of the greatest problems of the pharmaceutical drugs, with structural transformations between distinct crystalline forms, and this reduces the therapeutic efficiency. Also the low bioavailability, not only the low solubility in water and biological fluids, as well as the poor permeability across biological membranes. And for that, new formulation strategies can be considered, but also problems related with drug delivery, the poor drug delivery and drug resistance that reduce or eliminate the effectiveness of the drugs. And we and other research groups in last years try to consider the use of ionic liquids as a possible alternative approach to solve some of these pharmaceutical drugs. And looking for that, it's possible to consider like a third generation of ionic liquids, incorporating active pharmaceutical ingredients as anions or cations into the structure. In this cartoon, you can see the general idea. We can start from commercial available neutral pharmaceutical drugs, normally in crystalline form, and the pharmaceutical industry try to convert these neutral compounds into salts, normally sodium, potassium, or hydrochloride salts. In this case, we are trying to combine with biocompatible organic cations and trying to prepare amorphous salts. And using this strategy, it's possible to improve the solubility in water and permeability, the bioavailability and drug delivery, and also to eliminate the polymorphism. And in some cases, reduce or eliminate the drug resistance. This in particular for the case of antibiotics. We already proved this concept for several pharmaceutical drugs. And for today, I would like to present you first the synthetic part and some sustainable synthetic strategies. This is one of the possible synthetic strategies for the preparation of pharmaceutical ionic liquids using mechanochemistry. And in that case, we can compare the traditional method and the new method. In the traditional one, a large amount of solvent and time-consuming normally is required, comparing with this new method in absence of solvent or with a catalytic amount of solvent, and this is a faster process. And this works very well for some classes of pharmaceutical drugs, but in other cases, we need to use a traditional or some optimized synthetic methodology in order to obtain a stable and pure pharmaceutical salt in the end. Looking for and talking about cancer and bisphosphonates, bisphosphonates are examples of anti-resorption drugs. And we know that the bone is one of the most common sites for the development of breast cancer metastases, and this is a osteolytic nature. And these bisphosphonates are examples of anti-reabsorption drugs and normally can be used in the bone metastasis treatment. In this cartoon, you can see the action of bisphosphonates. Normally, they inhibit the osteoclast activity and promote osteoclast apoptosis, and they are released locally during bone resorption and at the same time concentrate under osteoclasts. And it's possible to form a new bone, regenerate new bone. But bisphosphonates may modulate the signaling from osteoblasts to osteoclasts. And the general chemical structure of the bisphosphonates is here present. It's possible to consider as a dianionic species, is resistant to hydrolysis with ability to functionalizations and enhance affinity for calcium to hydroxyapatite and inhibit the bone resorption. And looking for this general chemical structure, we can consider this carbon in the end of the bisphosphonate, in the middle of this bisphosphonate structure with different substituents, and according with the substituents, several examples of bisphosphonates can be considered. You can see in this list the simple one, ethidronate or chlordronate, until residronate or zoledronate, considering a heterocyclic as substituent. And at the same time, the relative potency is increased in this sequence. But one of the problems associated to bisphosphonate is related to is the pharmacokinetics, and in particular the very low bioavailability is lower than 6%. And in this context, we try to check the possibility to use ionic liquids from bisphosphonates. And we start considering 3 different structures of bisphosphonates: ethydronic acid, alendronic acid, and zoledronic acid, and trying 2 different synthetic strategies, using organic superbase like tetramethylguanidine or DBN for a direct deprotonation of these acids and the formation of the desired salts. Or alternatively, it's possible to use some organic cations like choline and 3-imidazole ion cations with ethyl and alcohol group or an ether group as substituents, in all of the cases as chloride salts. And then we need to convert these chloride salts into hydroxide using an anionic resin and form this cation hydroxide that can react directly with the acid, like a simple acid-base neutralization reaction in a quantitative yield and forming as byproduct only water. Using these 2 different sustainable synthetic strategies, it's possible to prepare different ethydronate, alendronate, and zoledronate based ionic liquids or organic salts, in some cases as monoanionic, and in other cases as dianion species. This depends the experimental conditions. And the yields are quantitative, and the purity is very high for this kind of salts. And using this strategy, it was possible to prepare 24 new compounds, completely characterized by the different spectroscopic techniques. And in general, the monoanionic salts are solid at room temperature, but the dianionic are liquid, are room temperature ionic liquids. And lower melting temperatures were observed comparing with the parent drug, the original drugs. But it's important to check the solubility after this manipulation, after this preparation of the salts. And looking for the solubility in water and saline solutions, it's clear significant improvement. The dianions normally are more soluble than monoanions. The bisphosphonates based on ionic liquids are significantly more soluble than the original bisphosphonates. And it's possible to consider this sequence. The alendronate based salts are more soluble than zoledronate or ethydronate. A significant improvement in the water and saline solution is clear, and this is a very important improvement, and 19 compounds are fully soluble in water or saline solutions. After that, we tried to check the cytotoxicity studies. This work was done in collaboration with Professor João Rodrigues in the Faculty of Medicine from the University of Oporto. And in this case, 4 different cell lines were selected, the fibroblasts as normal cells, and 3 cancer cells, the osteosarcoma cells, here mentioned as MG63, and this was selected because their known ability to disturb bone metabolism and increase bone turnover, and 2 other cancer cells, the breast cancer and lung cancer cells, here indicated T47D and A549, and this was selected because of their association with bone osteolytic metastasis. And it's possible to mention here, to put here in red, the most relevant results comparing the original ethydronate and after the preparation of the salts, also for alendronate and zoledronate. And these mentioned in red are better results comparing with the original drug, the original bisphosphonate. In general, it is observed an average to high cytotoxicity against cancer cell lines, and this is something that we are trying to check in more detail. It's important to conclude in this part that 24 new ionic liquids and salts from ethydronic, alendronic, and zoledronic acids can be prepare in quantitative yields and high purity levels. A complete characterization by different techniques can be done, and including a single crystal X-ray diffraction for the crystalline salts. It's possible to tune the water solubility and the thermal properties, and this is dependent of the selection of the organic cation and also the degree of ionization of the bisphosphonate, if we are using mono or D anions. Also, decrease of systemic toxicity and enhancement of antitumoral activity as low as nanomolar scale. And in a recent study performed in the Faculty of Medicine in Oporto, they check the ethidronate-based ionic liquids and show a higher anti-osteoclast and pro-osteoblast activity comparing with the original ethidronate or the simple protonated superbases. And this is an important point checked by modulation that now we are trying to develop in next months. In particular, in the case of zoledronate, this is a good example of the advantage to transform in this kind of ionic systems. It's clear the mitigation of polymorphism, the enhance of bioavailability, it's low toxic, and in particular for osteosarcoma cell MG63, two very promising salts were considered. One is choline in a mono cation combining with zoledronate, and the another is the imidazolium with an ether group, in this case as the dication salt. And this open new avenues for modulation of bone metabolism associated with bone cancer cells, in particular when increased bone resorption is present. And this is something that now we are trying to explore using other kind of bisphosphonates and trying to check some of the mechanisms associated of these results. But it's clear the main message of these pharmaceutical ionic systems is to start from pharmaceutical drugs, commercial available pharmaceutical drugs, and use as cation or anion in combination with appropriate biocompatible counterions. And using this kind of approach, new physical, chemical, and biochemical properties can be achieved. And in general, for most of the cases, it's possible to eliminate the polymorphism, to reduce the toxicity, to improve significantly the bioavailability as well as the therapeutic efficiency. And this is in line with a sustainable goal from Agenda 2030, in particular the goal number 3, in order to discover sustainable approach for pharmaceutical drugs for good health and well-being. And these ionic systems are a good platform for that kind of approach. I would like to show you other examples of this context, and in particular using anti-inflammatory drugs like ibuprofen and antimicrobial drugs like a beta-lactam, in this case ampicillin, or a fluoroquinolone, ciprofloxacin. In the case of ibuprofen drug, we are using as an ion in combination with a variety of organic cations, including some choline derivatives and ammonium salts, some imidazolium, in this case 4-imidazolium with different functionalizations, and the stylpiridinium. Different ionic liquids and salts based on the ibuprofen drug were completely characterized, and the higher solubility in water and buffer saline solutions were observed comparing to the free acid or sodium salt of ibuprofen. And here in this graphic, it's possible, in this figure, it's possible to observe the original water solubility of ibuprofen, 0.021 milligram per milliliter. The pharmaceutical industry tried to transform in sodium salt, and it's possible to improve until 333 milligrams per milliliter, but using our ionic system approach, it's possible to improve this water solubility, in some cases, higher to 5,000 milligrams per milliliter. Also, another important point, the majority of the cations and these ibuprofen ionic liquids were already tested did not affect the cell viability of human dermal fibroblasts and ovarian cancer cells, except for the case of stylpyridinium cation in some concentrations. It's important the development of sustainable synthetic approach for the preparation of this kind of salts. We are using an ionic or cationic resins in order to avoid impurities and to improve the stability of the final salts. We already test for a variety of beta-lactam anions in combination with different organic cations. In all of the cases, significant improvement of bioavailability and elimination of polymorphism is observed, and also it's possible to fight against the antibiotic resistance. Here to illustrate the examples in the case of ampicillin salts, a significant increase in the water solubility at 25 and 37 degrees Celsius, in particular for choline and 1-imidazole with an alkyl group. And at the same time, it's possible to enhance the eco-solubility and the octanol water partition coefficient. But it's also possible to improve the antibacterial activity of these ampicillin ionic liquids, in particular testing for 3 resistant E. coli bacterial strains. And I would like to emphasize the result of stylpyridinium ampicillin comparing with sodium ampicillin. It's possible to improve in one case 1,000 times and in another case 100 times in terms of efficiency, and it's possible to avoid the resistance problem of this ampicillin drug. But after that, we try to test other classes of beta-lactam, for example, amoxicillin or penicillin, and we try to develop and optimize synthetic protocol in order to avoid any hydrolyzation of the beta-lactam moiety. But in all of the cases, we observe the hydrolyzed beta-lactam base ionic liquid or salts, and 11 examples. It's very selective and very pure, the final compound after precipitation in moderate to high yields, and this is by neutralization of the basic ammonium buffer of these antibiotics in the presence of different cation hydroxide salts. And this is particular interest because it's possible to modulate or not the hydrolyzation, and we can try to check the antibiotic activity. And we check the antibiotic activity in these hydrolyzed examples of here mentioned as CICECO-amoxicillin and CICECO-penicillin, and in 3 examples with stylpyridinium and choline as cations, very strong antibacterial effects on sensitive and resistant E. coli and Staphylococcus aureus strains were observed. Here I would like to mention the results in red with 500 to 1,000 times better comparing with the original examples. More recent, we try to explore another beta-lactam, in this case cefuroxime, and here again a significant increase in water solubility and also in antibacterial activity, and this is again a work in progress. But not only beta-lactam can be explored, also fluoroquinolones, and in this case we are using ciprofloxacin and norfloxacin. It's possible to use as cations or as anions in combination with adequate counterions, and we can observe again a significant improvement in the water solubility. For the best results, it's 1,400 folds more soluble in water comparing with original drugs, and it's also possible to check the antimicrobial activity and cytotoxicity. And in this case, I would like to again to consider stylpyridinium ciprofloxacin against Klebsiella, that it's the best result, 20-fold decrease of the inhibitory concentration, and all of the compounds are not toxic to healthy cell lines tested. It is important to change the properties and trying to improve the therapeutic efficacy and bioavailability. And more recent, we try to combine mesoporous silica nanoparticles and some of these systems. And for that, we are trying to take advantage of the silica nanoparticle properties and our pharmaceutical ionic systems. we already functionalized the choline derivative cation and use ciprofloxacin as an ion, or the direct functionalization of ciprofloxacin in silica nanoparticles. And after the preparation of these materials, we already proved for different characterizations, and including TEM image, in order to prove the spherical nanoparticles and the average diameter that it's meters, and also to prove that the functionalization method do not affect the morphology of these nanoparticles. And our recent results related with this kind of materials, we observe for different microorganisms, and two very significant results: the silica nanoparticles choline with ciprofloxacin as an ion, and the ciprofloxacin directly functionalizing silica nanoparticles show very good antimicrobial activity for Staphylococcus aureus, comparing with free ciprofloxacin. And this is something that we are trying to explore in more detail. In general, in the antimicrobial ionic systems, the combination of antibiotic drugs as salts and ionic liquids show significant advantage. And also, if we are trying to combine with mesoporous silica nanoparticles, and this can open significant improvements for resistance and also for drug delivery. And this is something that we are trying to explore in ionic systems for pharma. More recent, in a FCT funding project, we are working in some active pharmaceutical drugs used for the treatment of tuberculosis. This is a work in collaboration with Professor Miguel Viveiros in Global Health and Tropical Medicine Institute from Nova. And we already test isoniazid and tambutol, and more recent meropenem. And the results are very promising, using similar approach that I already mentioned before for antibiotics, and more recent trying with mefloquine, that it's an alternative pharmaceutical drug, normally very effective for anti-malarian malarian treatment, but it's also interest for tuberculosis. And finally, I would like to show you a very recent project, the research for COVID, and looking for this pandemic, the COVID-19. We have this FCT funding project using ionic systems and similar methodologies that I already mentioned before, repurpose anti-malarian and anti-Ebola drugs as organic salts and ionic liquids in order to prevent and fight COVID-19. We start with chloroquine and remdesivir. Now we are trying to work with other pharmaceutical drugs. This project in collaboration with Faculty of Pharmacy in University of Lisbon and also Instituto Ricardo Jorge, and I hope to show results very soon about this project. Finally, I would like to present the Portuguese company named Solcamar that develop and commercialize different kind of ionic liquids, including task-specific with different counter-ions, and including for active pharmaceutical drug salts. For any interest or contact, you can contact directly to email address. And I would like to acknowledge the different collaborators in this work, marked here in bold, the funding from different projects, and thank you all of you for your kind attention.
Well, thank you, Luís. Thanks to keep it within time. We have now the session open for questions. If anyone wants to make a question, please raise your hands. Don't be shy. We have 10 minutes to do some questions. So now we have Sonia. Please, Sonia, go forward.
Well, thank you very much for the presentation, Professor Luís. I have more a curiosity, let's say. You mentioned briefly about luminescent ionic liquids. I'm correct, right?
Mm.
So those are ionic liquids that your company is producing to sell, or are just ionic liquid structures that you are trying to use and to develop something around? Because I'm really interested in this type of ionic liquids.
Okay, thank you for your question. Means the luminescent ionic liquids we are working in terms of research. We are working in different projects. In that case, we are using some commercial available luminescent probes that can be used as cation or an ion, or trying to functionalize in order to consider a charge. And in that case, we are using some luminescent in a project in order to check as contrast agents for imaging. And we are using also for detection in conservation. These are the two projects that are ongoing in the case of luminescent ionic liquids. Of course, looking for the question in terms of the company, it's possible to prepare task-specific luminescent ionic liquids according with the interest. And then, if you want, we can talk about that.
Yes, just a brief explanation, because we are working with some colleagues from the physics department. We are working the use of natural proteins as optically active centers to be implemented in luminescent solar concentrators. The problem is that we need this luminescence and fluorescence, but the stability of these compounds is quite difficult when we pass from the aqueous solution to, let's say, a solid state material. So in one hand, we are trying to figure out what we can do when we are preparing these materials to maintain the stability and mainly the photo stability of these of these proteins, of course. But then we can try to figure out or use another strategy. And this strategy can be, why not to use some of these ionic liquids to be our optically active centers, because then we just need to be sure that the compound is not being chemically degraded. But it will be easier because we don't have to consider the photo and chemical stability of a protein. That's why I was asking about the availability or not of these compounds, because I understand that you need to synthesize them, and I don't know if you will be interested in this type of approach for your ionic liquids as well.
Yeah, I think it's interest. Some years ago, we tried to prepare some intrinsically luminescent ionic liquids composed by metals, for example, ruthenium, more recent manganese, and some lanthanides. And in that cases, we observe in some examples, we observe like an improvement of the stability, the chemical stability. Sometimes this is important if you want to improve at the same time the luminescence of your material. But of course, it's important to discuss the best systems. More recent, we are working with organic probes. It means not with metals, but only organic luminescent materials.
Okay, so I can contact you later.
Yeah, of course.
Okay, thank you very much.
Ana Paula, please.
Hi. Thank you for your very nice and interesting presentation. My question is more about accuracy. It's about drug delivery systems. How ionic liquids can be used in this type of systems? You show an example about silica. The ionic liquid can be the active principle or a spacer or both. How can you use it in this type?
Thank you. From the beginning, before the use of silicon nanoparticles, we try to check the reason of some improvement, in particular for antibiotics, the improvement of the antibacterial activity. And for that, we observe that when we are using antibiotic, and in particular ampicillin as an ion in combination with some organic cations, a strong ion pair interaction can be considered, and in that case, the counterion, it's like a drug carrier. It means facilitate the transport of this pharmaceutical drug into the it means for the bacterial interaction. In the case of silicon nanoparticles, and this is a work now in the beginning, we have this significant improvement for ciprofloxacin, and we are trying to check because the silicon nanoparticles are not is not active in these examples. Ciprofloxacin, the activity in Staphylococcus is around 800 nanograms per milliliter, the value of the MIC, and we obtained 35. It means it's a significant improvement, and we are trying to check the reason. It's clear that we need to protonate it. If we protonate it, because we are using an ionic system, it's normally it's better if we are using like that. But now we are trying to understand the reason, if it's related with drug delivery, what is the reason for these results. This is something that we are doing in collaboration with other groups. Okay. I hope to answer very soon about that.
Yeah, I think it's a very interesting application. So thank you very much.
Welcome.
Marcia, please.
So thank you. It was a very nice talk. I have some questions or more curiosities. That is, before you measuring the physical chemical properties of the new AP ionic liquids, did you expect the results? Do you have, how do I say? Do you expect that some kind of ionic liquid family would provide better solubility of the new compound, or you just measuring, you see the results?
Thank you for your question. It means in the beginning, we try to test a variety of counterions that we have available, but now it's possible to modulate. It means we know how it's possible to improve parameters like the solubility or stability according to the combination, because we are using different families of cations with different functionalizations, and it's possible to modulate hydrophilicity or lipophilicity of this counterion according with the interest. It means it's not only to measure, we have the possibility to tune the properties according, or the results according with the combination, because we have now different pharmaceutical drugs already tested and different combinations, and these results confer some information that it's useful in order to design for future other the best combinations, the best cations and anions, and now it's not like trial and error. It's more specific, these kind of combinations.
Okay, thank you. So another question is, do you expect that the new drugs, the API ionic liquid, will develop new resistant bacteria?
If I expect in the beginning, it's
no, because you know there. For instance, you give the example of the MRSA bacteria. Okay, so what you told us that in this particular case, the new drug is more effective in killing this kind of bacteria than the other the traditional antibiotic. What I want to ask you is that for a longer exposition the bacteria to this new drug, do you expect that the bacteria will develop resistance to this new drug?
Yeah, for that we don't have any result until now in order to prove if yes or not, but it means all of this work is in collaboration with groups, other groups in microbiology or in biology, and they are very, it means they consider very promising the results, and now they try to change the kind of studies in order to understand if it's possible to eliminate resistance or not in a long period of time. And this is something that we need to check, in particular for beta-lactam, like amoxicillin, and this is an amoxicillin already hydrolyzed, and it seems more active than the original amoxicillin. And this kind of results are interesting to explore, but we need, in all of the cases, the background of our collaboration in order to prove if it's interest to explore more or not.
Just a final question. With the mesoporous silicon nanoparticles, did you change the functional degree?
No.
Okay.
Thank you, Marcia. Thank you, Luís. We need to move forward to the next speaker. Thank you again for this very interesting talk. I'm sure that a lot of people will contact you as soon as the workshop ends to continue the discussion, because it's a quite interesting topic. Thank you. So now we can move forward to the next speaker. It's also a pleasure to present José Esperança, a principal researcher at REQUIMTE, in the lab REQUIMTE. In research, interest on ionic liquids is very wide in terms of it comes from synthesis, characterization of ionic liquids, physical chemistry, and both pure ionic liquids, mixtures, and the application of ionic liquids in different applications, namely gas hydrates, on research fields like extraction, separation, electrochemistry, carbon dioxide capture and separation to the gas and oil industry. Today, José Esperança is going to present us on something about the manipulation of the ionic liquid structure in order to enhance their applicability in valorization processes, and how we can design and how we can conceive an ionic liquid specific task. Please, José, the floor is yours. The virtual floor is yours.
Okay, Pedro, thanks for your kind words. I was supposed to bring here the materials that were related with the project. Of course, due to COVID and due also to some delays in the characterization, I decided to bring other part of our work that we have also done the beginning just by ourselves, but in the end in collaboration with Mara and Anna, and then I decided to bring this work to show you. It's important to say that I decided to skip most of the introductory part about ionic liquids. I was already betting that Luís would present some short introduction, and then most of you already know about ionic liquids, and then those introductory slides, I decided to skip them. Now, based on that, and because we are talking about manipulating the structure, what I decided to bring was about increasing the alkyl chain length, changing functional groups, increasing the number of, in this case, OH groups, it can be something else, and by the end, an application with aqueous biphasic systems and some final remarks. First is the effect of increasing the alkyl chain length. It was an old work, and the important here is to place this work and why we have done it. In the beginning, we were just playing with alkyl chains, changing the choline cation and starting increasing this alkyl side chain to see, because we were working a lot in liquid-liquid equilibrium, how this would affect the equilibria with water and with other solvents. And in this case, we were playing with bisturiflamide, and everything that I bring here today is about bisturiflamide on ion, okay? Why? As you will see along the presentation, this is one of the most hydrophobic anions. And then what we wanted was to play with it to understand how we could make it much more soluble, and if we would be able to make it enough soluble that it would be completely soluble in water, and we could use it in many applications that where they are not, it's not possible to use this anion because they are not soluble in water. In this work, of course, the results are what we expected. We got some UCSD type phase diagrams. When you warm this, here you have temperature. When you warm the solution, you go from 2 phases to 1 phase. And of course, when you increase the alkyl chain length of the cation, the envelope of phase just goes up, and the immiscibility is worse and worse. Then what we have done afterwards was to start checking, because this was with water, and then what happens when you put an alcohol. And in this case, we decided to use, of course, we used other alcohols, we used a lot of things, but the results that I'm presenting here are with octanol. Why octanol? Because you have also an OH group there, right? And you have a long chain. And as it's so, again, as expected, what you see is that when you increase the alkyl chain length of the ionic liquid, you increase the miscibility, the UCSD goes down, and this happens due to the large CH chain here in the alcohol that needs, of course, and likes the longer alkyl chains here in the ionic liquid, and it needs those non-polar domains to dissolve. And then, because we were just playing with different solvents, we just came to some ethers, and we were also testing them with a variety of different types of ethers. Okay, and those are the results. We tested with 3 different colinium-derived cations, with C2, with C5, and with C8. And this is what was not expected at the time, because what we got was LCSTs. And what is this? Is that you go from 1 phase to 2 phases when you warm it. By and large, you just get the mixing while you warm the solution. Is the inversion of behavior that you saw in the UCSD. And what we have seen is that for most of the ethers, this is the type of phase diagram that you have. Okay, you can also see that when you increase the alkyl chain length, you enhance the miscibility, right? In this case, the curves just go up, and then it means that the 1 phase region enhances, and then the miscibility enhances. Is just the opposite as you would get with the UCSDs. We, in collaboration with Zenon Canongia-Lopes, of course, we just did some molecular dynamic simulation to try to understand why we were getting these results. And of course, the first one is that higher solubility and LCSTs as you get in this direction, right? C8 better than C5, better than C2, and it's because you have large non-polar domains where the ethers can dissolve. Then we decided to start comparing the size of the chains, and the interesting thing there was that methyl esters would dissolve better than ethyl esters in all the ionic liquids. And this was a bit strange, because you have there the non-polar domains, then it wouldn't make much sense that with a bigger alkyl chain here, you wouldn't be able to dissolve it. But then what we were able to see was that it is very important, the interactions, the H-bond interactions between the OH of the cation and the oxygen atom in the ether. And then what it happens, as you can see here, is that the accessibility of these oxygen atoms is much better when you have a short chain here than you have when you have, for example, just an ethyl. It's a a very small change in here in the size of the chain, but the accessibility of this oxygen atom worsens a lot. Then the third one was just about more compact chains versus long alkyl chains, and the results just show that more compact chains are better than long alkyl chains. But this was just the beginning, and at this time what we just looked to the results, and what we have seen was that when you have this choline cation and ethers, you get LCSTs. But what if you just change the OH group from the cation to the molecular solvent and you put an ether group in the ionic liquid? And that's what we did. What we did also at this time, we were calling it similar sized ammoniums. Why? Because everything else is similar, and here what we did was to consider the number of heavier atoms. We just discarded the hydrogens, of course, and you will have 3 carbons, 1 oxygen, here 3 carbons, 1 oxygen, and here 4 carbons, and that's why we called similar sized. You'll see that this is not the case anymore. And here you have an OH group, here you have an ether group, and here you have just the alkyl chain. This is just another way to see it. And then we decided to go again and test it with the same type of materials. And the results that you have here are for alcohols, most of them, right? It depends on the size of the alcohol and everything. I will not get into detail there. And you have water, those ones, right? And you have the ether here. You have just part of the curve because it goes to very low temperatures in most of the cases. What we have seen, and the most important lesson that we took from here, is that the important thing that controls the UCST, LCST in this type of phase diagrams for this family of ionic liquids is the molecular solvent. We always got LCSTs with the ethers, when as molecular solvent, we always got UCSTs with amino alcohols, diols, alcohols, whatever you tested. And that's the main lesson that we got from here. Then, as I told you in the beginning, we were looking for ionic liquids with bisterifilamide anion that were completely soluble in water. And then, of course, what to do? And we just played with the number of OH groups that you have in the cation. Okay, we started with 2 OH groups, right? And then we came to 3, and of course we did with different sizes of alkyl chain also to test the results. And this is the most relevant result that we got, because in some cases you have always UCSTs, right? And what we see is that it's possible to decrease the temperature up to here 320 Kelvin. But this is the most important part, is that we were able to synthesize 3 of them that are completely miscible with water at room temperature and even below when you cool it down until they just solidify. Why we were testing also with bisterifilamide and this type of cations? As some of you probably remember from works, I think they were from Watanabe or Ono, they showed that several times ionic liquids that show LCSTs with waters. Well, not many, but a few papers. In those cases, when they talk about what you have to do to get the LCST of an ionic liquid water, they just say that they join usually phosphonium, that it's quite hydrophobic, with some hydrophilic anion, and that's how they usually say that they just get to LCSTs. It doesn't work every time, but that's how they do it in most of their papers. And then that's the same concept that we tried here. We changed the hydrophobicity to the anion, and we kept the hydrophilic cation increasing the hydrophilicity, trying to see if we could also get different behavior with LCSTs. And we were not. We just got UCSTs. The only good result was that we were able to find some NTF2 ionic liquids completely soluble in water. But we wanted to understand why we were getting these. And again, simulations from Molecular Dynamics, from Zenon, Canongia Lopes, showed that this is the simulation for the colinium cation when with NTF2, where the green depicts the polar network. You have it here. OH-OH cation light blue is the cation hydrogen bonding. You have the results here. I'll show you afterwards. Then you have another pictures where you have the cation and H2O, the hydrogen bonding network in the aqueous mixture. And then these Ni that you see here are the values that correspond to the average number of neighbors of a given ion and the molecule within the aggregate. In this case, the pure colinium NTF2 ionic liquid is composed just of a continuous polar network. Each ion has a number of contact points in the first shell of 5.93. That's what you have here. The OH groups of the ethanol moiety, you see here, are mostly isolated, 68%, or forming only very few connections between them, cation-cation, 22% as pairs, 6% as trios, with a number of contact points of only 0.37. It means that the OH from colinium, they do not interact much between them. And the solubility of this compound is rather poor because the water molecules are not able to disrupt the polar network and solvate the NTF2 anions. Here you see for the example with 3 OH groups. And what you see is that, of course, there is still the polar network here, continuous, but with the small number of contact neighbors. And you have the 3 ethanol moieties can also do a continuous network of H-bonded OH groups, each of them establishing 2 H bonds with the neighboring OH groups, Ni 2.12. It means that there is much closer contact between these OH groups, cation to cation interaction. And now we did also a simulation. It was at about 50% IL in mass percentage of water molecules. And what you see is that the water molecules also form continuous H-bonded network with the OH groups of the cation. You have it here, right? With a number of 4.53. And the number of H-bond clusters formed exclusively by cations is now very small. You lose all the interactions between cation, right? This plot comes to the left. It means that the OH of the cation are alone, are not interacting with other OH of other cations, but because they are interacting with the water, and this is the reason why you have this compound completely soluble in water. By and large, the driving force that regulates this is the ability to compensate the penalty to solvate the NTF2 anion with an enthalpy gain related to the integration of the cation on the water H-bonded network. Okay, and that's the reason why you get it. When we started doing this and we started close similar sized cations, we were thinking just in the number of heavy atoms. In this work, what we have done was, of course, we did a lot of characterization and at some time we just start looking at the increase in the size of the ionic liquids, as you know, as most of you know for sure. And it was usually to hear that an ionic liquid, when the alkyl chain increased by CH2, you would have on average 17 cubic centimeters per mole. That would also increase the volume of the ionic liquid, the molar volume. In some cases it's just 15, it depends on where the substitution occurs, but In most of the cases, it is known that to be about 17. What we have done was to compare also with the cases of the two ionic liquids with more OH groups. And what we see is that we are adding a CH2 group, but we are adding also an OH group. And what we see is a value that is quite close to the 17 cubic centimeters per mole per each CH2. That's what we have here, delta V per delta M. And the same when we increase again with another OH group. And what we see is that the OH group there, it's like if it has just zero volume. Then we just came back to the ionic liquid that we did with the ether chain. And what we have seen when you do just differences between ionic liquids is just the oxygen in the ether accounts for 6 cubic centimeters per mole. And this was also confirmed by results of other authors when they have, for example, 2 oxygens in the same chain of the cation. And if you just do calculations here, you increase one CH2 with 17, and you increase 2 OH, that is another 12, then it's 6 per each oxygen there. Now, how to explain this? We just got van der Waals volumes of these groups that you see here from the Lennard-Jones diameters and from the CH, CC, and CO interatomic distances, and is already known that the real volume is more or less 1.6 times these van der Waals volumes that you see here. And this is confirmed when you do it for the ether, the oxygen in bridge, like an ether, because it's like 3.5 times 1.6, and you have the 6 cubic centimeters per mole that we got before, as you have seen. But in the case of the hydroxyl group, what you see is that you have this difference. When you multiply this difference by 1.6, you should get around 5 cubic centimeters per mole. It's not what we got before. And this is what we try to explain what happens. And what happens is very easy, is that you start having much more hydrogen bonding, and then these interactions just contract the free volume, the ionic liquid, and changes this volume contribution of the OH group. It means that the contribution should be, if you would neglect the OH bonds, the OH contribution, the hydrogen bonding contribution, 5 cubic centimeters per mole, and in this case, it's about 0, right? Now, with the ionic liquids with NTF2 that are completely soluble in water, of course, it would have to come to our attention, and once in a discussion with Mara, that it could be interesting to try them in aqueous biphasic systems. Why to test them in aqueous biphasic systems? Because we are talking about ionic liquids that are soluble in water, but of course they are very close, or at least close to phase separation. And then it could be, we could have the chance to use some type of instead of using salts or polymers, try to do aqueous biphasic systems with easy things like carbohydrates or glycerol or whatever. And that's what we started doing. But to do that and to be able to have a possible application, the first thing we decided to do, and Anna did it, was to test their cytotoxicity. We just did with CACO2 cell line, and the results are the ones that you see there, and they were very interesting. We were expecting that they were slightly more toxic, because you were talking always about NTF2 anion, and usually ionic liquids with NTF2 anion would be more toxic, and that's another reason that why they are not much used. And the results that we got with this cell line, of course, we will have to test it with different cell lines, with other types of bacteria, with fish, with many other types of toxicity studies. But at this stage, what we have seen is that they have EC50 values that are very good at about 30 grams per liter. The last one seems even better, but taking into account the standard error of the measurements and everything, we should say that they are all similar, and they have EC50 values at about 30 grams per liter. Now, because they had low toxicity, we started to try them in aqueous biphasic systems. And we did it with carbohydrates, monosaccharides, disaccharides, polyols, different types of molecules. But what I'm showing here is just one example, and of course I'm putting more emphasis on the ionic liquid than on the type of carbohydrate. And in this case, what we see is that the red symbols correspond to this short alkyl chain with 3 OH groups. Second one, the green, is 2 alkyl chain 2 and then 3 OH groups. And the last one, you have just 2 OH groups and 2 methyl groups here. And what you see is that there is a change from that corresponds to the hydrophobicity of the ionic liquid. With the one with 3 OH groups and a shorter alkyl chain more to the right, and the other ones more to the left, and are the more interesting ones because you need less quantity of carbohydrate to get the phase separation. And this is just an example of a possible that we tested also in Mara's group over there in Aveiro, about the separation of carbohydrates from antioxidants from a vanilla pudding waste, just to try to get the separation of antioxidants in one phase and carbohydrates in the other phase. And the results were very interesting and open up the way to test in much more applications. Final remarks, just that the liquid equilibrium experimental results that we showed are mostly UCST type phase diagrams with both water or alcohol. LCST type phase diagrams were only observed when you have ethers. Ionic liquid is not able to control the change in this type of phase diagram, unfortunately. That's what I would like to see. And the number of ethanol groups there allow to control the hydrophilicity or hydrophobicity of the ionic liquid, and in some cases we can even make it some bisulfamide based ionic liquids completely soluble in water. And we did MD simulation to try to understand why this was happening, and by the end we also opened the door to the use in some processes, for example, aqueous biphasic system separations, as you have seen here. I want to finish by acknowledging, of course, my group here at FCT Nova that worked in this project, and also the group there in Aveiro, Mara's group, and including Ana Souza that did all the cytotoxicity studies, and of course, Fundação para a Ciência e Tecnologia for financing, and my kids, of course, because they are the reason to perform all this. Now, for the ones that don't know, I work now in Faculdade de Ciências e Tecnologia in the other side of the river, and is just close to the river and close to Costa da Caparica Beach. And this is our campus at FCT Nova. In terms of research unit, I work as Luís in Laboratório Associado para a Química Verde, REQUIMTE in FCT Nova. And that's it.
Thank you, José. So now the session is for questions. Please raise your hand. So I have Mara.
Hello, José.
Hello.
Thank you so much for your very interesting talk. In reality, I was missing this type of liquid-liquid equilibrium from my past life, or my previous life. Now it's too much applied. Well, I have one question, and I don't know if Ono already did it, and if I'm missing some papers that he has been publishing or not. We can have ionic liquids or design ionic liquids to have a LCST or a UCST behavior, right? For instance, keeping the NTF to an ion and changing the cation. So if you introduce a phosphonium cation, you will have lower critical solution temperature behavior.
But not with NTF2.
But not, oh, it's an hydrophilic cation.
You need an hydrophilic cation, yeah, an ion, because you have the hydrophobic cation.
Hydrophobic cation. So what happens if you mix their two ionic liquids with a common hydrophilic ion, but with two cations that have opposite behaviors? Do you think that we will face the double salts theory? Or do you defend the theory of Robin Rogers or that of Tom Walton? My question is, if you mix them, let's say at a 50% molar ratio, what is the behavior in terms of liquid-liquid equilibrium with water? I don't know if there are any data in the literature, but I'm just wondering.
I don't remember to see. One of these days we were also discussing that because we were thinking if we should try to mix it or not, because we were looking, as you know, from the work of Hector, right? He has a lot of different examples of mixtures of two ionic liquids that do not mix, right? And the question is that I don't know if you mix those ionic liquids with three OH groups with phosphonium, right? With the same anion, it can be NTF2 or it can be something else. What will happen? Right, what you're saying is you have the NTF2 anion, right? And then you mix with two completely different, right? Phosphonium or these ionic liquids.
Yes. On
the other, we were discussing because we were eventually trying to test it, because I think they can somehow phase-separate, because I think that the phosphonium cation does not like the ammonium cation with three OH groups there, and I don't see that they can interact between them.
But for instance, if you mix tetrabutyl phosphonium chloride with imidazolium chloride, one of them, you will have critical temperatures or low critical temperatures, and you will have one facing the lower critical solution temperature behavior and the other facing the upper critical solution temperature behavior. Well, of course, the mixable ionic liquids, and to avoid that, we can't mix phosphoniums with ammoniums, but we can mix phosphoniums with imidazoliums. Can't we?
No, if we mix the phosphonium cation with the imidazolium cation with chloride, but I think the phosphonium chloride is not an example of FLCST. In his cases, I think he goes always to I think it's amino acid anions and stuff like that. I don't know by heart, I don't remember now, but I know that are just some special cases, not all the phosphoniums are.
But the question persists. You can mix those with a common anion and change the cation.
If you change, but most of them are just soluble in water, and the ones that if you mix with an anion that is soluble in water, they are both soluble in water, and I'm sure that you get, if you can get it, you get just a new UCST. If they are insoluble, most of them have UCSTs also, then that's not a point, right? Only if you could find one that shows an UCST, one that shows an LCST, and it's not easy.
But it will be loved.
That's why I'm saying that I would like to see, well, first would be if they would mix, what would happen, right? But I think they wouldn't even mix. If I mix some phosphonium and TF2 with some of these with 3 OH groups and TF2, I'm not sure if they would mix. Probably no, they would phase separate. Maybe I'm wrong, I don't know.
I will tell you that because it is a work of Elena. We already have some evidence on that on aqueous biphasic systems. If you mix 2 ionic liquids with a common anion, but that it will be easier. What you have is odd behavior when one ionic liquid prevails over the other. So you will have the salting out or the phase separation of the first ionic liquid, and then you will face the phase separation promoted by the second ionic liquid. And what I'm expecting to see in your phase diagrams, it's something that changed from the upper critical solution temperature to the lower critical solution temperature. But yes,
but we would need to find the right set of ionic liquids. That's the point. That's the point, yeah.
Thank you so much for your nice presentation.
Thank you, Mara. Any more questions? Well, I have one, if I may. Well, on the work that you studied the change on the molar volume by replacing the CH2 groups by OH groups, I'm assuming that you measured the density data, right?
Yeah, of course.
And all your discussion was based on entropic effects, on the interactions that are able to be done on these new structures. But did you consider entropic effects to have this change on the molar volumes? Because let's be honest, so having several OH groups instead of a CH2 and having the same change on molar volume is quite surprising.
Well, I think, well, the main reason is about the interactions, right? It's just the hydrogen bonds that are stronger, and then everything gets together, right? It's that what makes the...
Well, if I understood correctly, you said something about the hydrogen bonds are more favorable, and the ionic liquids are able to, or are prone to establish new hydrogen bonds with the surrounding molecules. And by that reason, they should have, we are expected to have a lower volume. Shouldn't we expect the contrary? So if the molecule is prone to have hydrogen bonds with the surrounding molecules, the charge dispersion to be higher?
Sorry, Pedro, I didn't understand that.
So well, in terms of volume, we would expect to have an increase of the ionic liquid volume.
Well, the point is, when you have just the one OH group, as you have seen in the simulations, what happened is that they do not interact with cation, right? They just interact with the NTF2. In the case of the ionic liquid with 3 OH groups, what you see is that the OH of each cation interacts with other 2 OH from other cations that are just in the surroundings, and this means that they have to be closer, right?
Sure.
And I think that's the reason why they have higher density and everything, and then when you convert to molar volume, you see that the contribution is... It was surprising for us, of course. Also.
That is exactly my point. So what you are telling is that you have better interaction between the ionic liquids, so you have a better packing, and as a result, you have a higher density, and then you have that effect on the molar volume. But that doesn't translate exactly to the change of the volume of the CH group to the OH group.
No. What it means is that if you would have, imagine that when you have the ether, right? When you have the O in bridge, what it means is that there is an increase that is 6 cubic centimeters per mole, okay? When you have OH group in the end of the chain, right? Alkyl group there, hydroxyl group there. What you see is that the change in molar volume should be around, let's say, 5 cubic centimeters per mole. And you see this because if you compare alkyl molecules used by the molecules, you see that the difference in molar volume, in molecular volume, it's about 3, I think it's 3 cubic centimeters per mole based on van der Waals diameters and the distance of the interactions, right? And you know that usually this reflects in 1.6 times these van der Waals volumes, and then it means that it should be around 5 cubic centimeters per mole. What we are saying is that instead of having an increase due to the OH group of 5 cubic centimeters per mole, you have 0. It's like if the OH group is not there, right? Why? Because everything is packed together, as you said, and everything is closer. Then it means that there is a contraction in volume that it's just by chance. It could be -2, it could be 2, it could be whatever. It's just a curiosity that it changed to 0. It's like it annuls the 5 cubic centimeters that it should increase. That's 0. There is no reason to be 0. It could be -2 or it could be 2. Doesn't harm. Okay. It's just interesting that it happened. Once it's not in that table, but I think once we also tried to see with an imidazolium ionic liquid with OH group, the problem that we have is that in many cases it is difficult to trust in all the densities. If you have some ionic liquids with OH groups there and you trust the densities, I think we tested and in one case it worked, in another it doesn't. But when you look to the densities, it doesn't make any sense. And then we did decide not to compare because you would have to choose one and someone would say why you choose this and not the other. And then we decided to keep it apart. But if you have data of imidazoliums with OH groups there, and you trust the density, just check it.
Okay, thank you very much. Thanks again for your very interesting presentation. We have now a break. Now it's not a coffee break, just a break. You can have water or coffee, and we'll be back here 4:10. Thank you all.
Thank you. See you.